Oh, hi, thank you very much for the invitation to speak here, and thank you for the introduction. Yeah, so today I decided to talk about the this recent work that I did with Stephen Cameron, who's currently a postdoc at the Quran Institute, and if I have time, I may also talk about joint work with Eduardo Garcia Juarez at the University of Barcelona and Yoshio Mori, who's a colleague at my university, University of Pennsylvania, on the fully nonlinear 2D Peskin problem. So since this is maybe a little bit away from the main theme of this conference, I hope you don't mind if I give you a little bit of an introduction to the situation that I'm discussing, more than I might have if I was talking about relativity. So the types of problems that the family of problems that I want to discuss are sort of PDE dynamical mathematical models for the evolution of what's called a free boundary. So the boundary is a thing that's changing in time, and examples of situations where this comes up are typical Kelvin-Helmholtz, the water wave problem, the Hilly-Shaw cell, and the situation that I'm going to tell you about today is really the modeling of red blood cells flowing through the heart. And this is kind of a new, it's not a new equation, but it's a new direction in the analysis of PDE studies in free boundary problems. And I'll explain that more later. So the main interesting questions are, if you start with a boundary, and here I'm just drawing a 2D boundary, but you could have a 3D boundary or a higher dimensional boundary, and it evolves over time by some dynamical law, then it turns to a different boundary as time evolves. And things you want to understand are local and time existence and uniqueness, regularity of the existence, does it have smoothing effects or not? For certain situations, do you have global and time existence and uniqueness? And what is the large time behavior for T large of the boundary? Does it exist globally? Does it blow up? What happens for non-small initial data is another important question. And how does the nonlinear effects come into play during evolution? Also studying the local and global existence at so-called scaling critical regularity is a widely studied topic. And lastly, the non-local effects due to viscosity come up a lot and are an important area of study for these types of models. And so some examples are first is the sort of incompressible porous medium equation. And here you have the porous medium equation up top with dg rho plus u dot grad rho equals 0. And you have a divergence free condition gradient dot rho equals 0. And you have Darcy's law, which is the velocity is the minus the gradient of the pressure minus the density rho, with the density is pushing down due to the forces of gravity. And a typical picture of where these kind of dynamics come up are in a porous medium, where the gray areas, there's no dynamics, and in between them the dynamics are happening. Okay, and another related example is for the incompressible porous medium equation is the Hilly-Shaw cell. And here you have this relation that looks like Darcy's law in 2D. And the sort of picture is, if you have a fluid, you have two fluids interacting between two large thin plates, like as in this picture. So where you do a typical type experiment like this, and you look at the dynamics and what happens over time. And another example is the Muskat problem that I've studied actually quite a bit, which is, so you have two incompressible immiscible fluids. Mu is the viscosity, and rho is the density, and they you have a fixed density in like an inside and outside domain, D1 and D2, but those densities can be different and similar for the viscosity. And so there are two basic cases that where the boundary is a circle or a closed curve, as in this first case, and the second case is where the boundary is a curve or a surface. It's typically vanishing at infinity. And yeah, those are the two cases. And so just in pictures, Muskat was a petroleum engineer, and he was interested in pumping oil out of oil sands, and that's how this equation got derived. And these are some interesting structures that you see in a Haley-Shaw cell experiment, and you also can observe sort of viscous fingering. And these are the kinds of physical phenomena that are being modeled by these equations and the free boundary problems. And so the Peskin problem, which is was named after Charles Peskin, is as it was widely called the Stokes immersed boundary problem, and it was it's modeling in contrast, it's modeling blood flow through the heart and the behavior of red blood cells moving through the heart. And so several weeks ago, I gave this talk, or I gave a talk about these results, and to a PDE analysis audience, and I got the question at the end of the talk: is this a model that you're studying of interest outside of mathematics? And so, rather than try to convince you of that, I added the slides to my talk. So these are the so Peskin, Charles Peskin really sort of introduced this study in starting with his PhD thesis, and this is in 1972 PhD thesis, flow patterns around heart valves, and it really became a computational method that's widely called the immersed boundary method, and this is kind of a sampling of some of his papers on the subject. So this is his thesis, and this is a paper that came out of his thesis, and flow patterns around heart valves and numerical method. And this is a later paper about numerical analysis of blood flow in the heart. And this is a more recent paper summarizing the immersed boundary method. And so rather than just try to convince you that this is widely studied outside of in the computational world and the engineering world and in the medical world too, I'll just sort of show you the number of each one of these papers is like massively cited, and this you can see the citations for the immersed boundary method on MathSciNet versus sort of in Google Scholar. So there's a lot of citations. And there's some inflation in Google Scholar, but also it picks up a lot of citations in all over science, not just in mathematics, whereas MathSciNet just picks up citations in mathematics. So yeah, I just wanted to briefly convince you that this is an important model in a lot of areas of science, even though it may not be so widely seen in sort of an analysis of PDE community until recently. Okay, so the Peskin problem, which is typically previously been called the Stokes immersed boundary problem, takes the form that I'm showing you here. So you have the Stokes, you have a boundary, and say the domain is outside, and then there's the domain inside is the complement, and it's like R2, not not including the domain or its boundary. And so you have an open domain denoted D and D complement, and you have a velocity field U, and you have the boundary is gamma, and the points on the boundary are parameterized by X. So the position on X is parameterized by this capital X, which is a vector, and it's a function of t and theta. And the problem is to find the velocity field U and the elastic string position capital X dynamically over time. And so this can be formulated in the PDE way as an immersed elastic string. So you can look at it as a Stokes fluid with viscosity mu. So mu Laplacian U minus gradient P equals 0, and you have a divergence free condition Laplacian U equals 0. And you also have jump conditions. So this stress tensor sigma is the viscosity times gradient U plus gradient U transpose minus the pressure. And then N is a unit normal vector on the boundary. And then the jump of that is equal to F, where F is a tension, F is the force times the vector of the derivative of X. And we also have the no slip condition that the jump across the interface of U is equal to 0. And these are the two jump conditions, and they represent the no slip and force balance boundary conditions on the interface. And then the general tension force law for T an arbitrary nonlinear function is that the force is equal to the theta derivative of the tension of the absolute value of X times the unit vector derivative of X over the length derivative of X. And the simple tension force law is basically T equals kappa 0, where T equals K0, where K0 is a constant. And then you get the simple linear force law that F is K0 times the second derivative of X for some physical parameter K0. Okay, so this is one expression of the PDE model for the boundary. The second formulation that sort of made this model famous in the computational community is the immersed boundary formulation. And so you have the same picture, and the immersed boundary method is basically this equation. It says that Laplacian U plus the gradient of the pressure is equal to the integral of this is the force again, as I wrote on the previous slide, so the derivative of the tension times the unit vector of the derivative of X times a Dirac delta function of X, which is the variable of the these quantities on the right hand side, minus boldface X, which is the position, and you integrate this over theta. And you also have the divergence free condition. So in this situation, the force balance condition at the interface gamma is treated as an external singular force field supported on gamma, and the no slip boundary condition is satisfied automatically. It's built in, and so this is this formulation is very useful computationally because it's sort of split into two equations. The left-hand side is in physical space, and you can estimate it, and the right-hand side is sort of integrated over the particle space, and you can estimate that separately. And so this formulation has proven to be extremely successful computationally, and it's probably the main reason why this model was so widely studied computationally. A third formulation that's very useful for analysis is the contour dynamics formulation. So when it says that the string moves with the flow, so the time derivative of capital X is equal to the velocity evaluated x and over time, and you can invert the Stokes operator in the whole space, and you'll obtain this model for both face x, and it's dtx is equal to the kernel g of x at theta minus x at alpha times the force integrated over alpha over all possible positions. And here G is called the Stokes lit, and it's minus log times the identity matrix on R2 plus the unit vector X tensor itself in R2. So this is a contour dynamics formulation that's proven very useful, both for numerical purposes, both for numerical computational purposes, but also for analytical purposes. Okay, so here's a simulation that so I started working on this when my colleague Yoshiro Mori moved to UPenn a couple of years ago. He was interested in discussing, and he's an applied mathematician, but he's very interested in analysis and improving things. And he does math biology. He has a MD degree and a PhD, and he is very interested in sort of understanding why things happen, improving things, and also trying to prove things in biology that people don't really feel like that. Yeah, so he's interested in proving things, but including analysis of PDE. And so we started talking, and he got me interested in this problem. And he also does simulations, and this is these are some simulations that he did for the Peskin problem. And one of the things he observed is that there's low order numerical convergence rate for the immersed boundary problem. And the computations above are done by Yoshiro Mori in 2008. And these sort of spikes near the interface sort of illustrate that the convergence rate near the interface is not fast. And so applied mathematicians such as Mori and also Johnny Guzman and others have expressed the interest of seeing future analytical work for this model. The low order numerical convergence means that existence and uniqueness results with low regularity can be very useful, both for theoretical justifications, but also perhaps for motivations to develop new numerical schemes. Because if you have a low order convergence, then you wouldn't expect a high regularity theory of solutions to be explaining the numerics that you're doing. The lowest regularity perhaps that you might expect for well-posedness is probably scaling critical regularity in some sense. So this is what we are interested in. I'm going to talk about critical local well-posedness for the fully nonlinear Peskin problem with the general potential law. But first, I want to show you a few references for Muskat at critical regularity. Prior to that, I want to have a drink of water. Okay, so for the Muskat problem at critical regularity, there's really a lot of results. I'm just going to mention a few. First, this paper by Constantine Cordova, Gancedo, and myself studied global existence for the Muskat problem and scaling critical Wiener algebra spaces in 2013, and in 2D, and then in 2016, we did similar results in both 2D and 3D. And this recently, there's been sort of an explosion of interest in the Muskat problem, which is a related model. And one of those papers is Nguyen and Passador introduced a paradifferential approach for well-posedness, and they studied the local well-posedness for slightly subcritical initial data. And then Mugen studied the well-posedness with surface tension, and then the same Wynn studied global solutions to the Muskat problem in this scale and critical Besov space, B.1, infinity 1. And then, so this is Hui, Wynn, and then there's these 3 very interesting papers by Alazard and Kwok Hong Wynn on critical local existence for the Muskat problem. They sort of use this trick of studying the problem with initial data that's logarithmically supercritical, logarithmically subcritical, and then you can use that logarithm and to actually there's a sort of there's a theorem of Lebesgue that says that if you're integrable, then you're actually slightly more integrable up to some logarithm of a weight, and and they use that trick to sort of go from logarithmically subcritical local well-posedness to critical local well-posedness. And these are very hard and interesting papers, and I don't want to seem to be oversimplifying them by describing that trick, but it is, so they do local well-posedness in 2D and 3D, the critical regularity. And now I want to discuss some PDE analysis references for the Peskin problem. And so there is a huge literature on the Peskin problem in the computational world and in the medical world and in engineering and other worlds. But these are most of, other than the 2 papers that I wrote on the subject with collaborators that I told you at the beginning, these are all the papers on the analysis of PDE for the Peskin problem. So the first 2 papers are really by Mori, Rodenberg, and Spern. Rodenberg was a PhD student at Minnesota of Mori, and they proved local and global well-posedness for the Peskin problem in slightly subcritical Holder spaces. And then Lin and Tong prove similar results, local and global well-posedness in Sobolev spaces like H5 which are not slightly subcritical. And then Tong studied the convergence of the regular Stokes problem. And Gancedo, Belenchon, and Scarbonia studied a model problem that they called the N-Peskin problem, and they proved global existence in the Lipschitz class. And Chen and Kwok Hong Wynn studied the Peskin problem with B.1 infinity initial data, and this is like a huge space, and they prove local well-posedness and global well-posedness for small data in this very large space. I should say that all of these results work in the case of a linear tension, so the simple tension law. And so what I'm going to be talking about is the first result for the fully nonlinear tension law with critical regularity. Anneliese Rodenberg did in her PhD thesis extend these results to the local well-posedness and slightly subcritical spaces for the slightly subcritical Holder spaces for the fully nonlinear Peskin problem. But in that result, she was not, the method that she used, they were unable to prove the smoothing effect. So this result proves the C infinity smoothing effects, but the in her thesis, the way that it was done was unable to establish the smoothing effects. Okay, so let me tell you a bit about the boundary integral formulation for the Peskin problem. So this is the boundary integral formulation for the general force law. So you have the time derivative of x is the Stokes lit g of delta x times the derivative of the tension t times the unit vector d alpha integrated over alpha. And here we write x prime as a derivative, partial theta of x. And we use a standard partial difference operator. Delta alpha is delta alpha of x theta is x theta plus alpha minus x theta. And for z and R2, g of z is the Stokes lit, which I'm going to decompose as g1 plus g is equal to g1 plus g2, where g1 is minus the log, and g2 is the unit vector z tensor with itself. And okay, so in the simple tension case, the tension where all the previous results I mentioned take place, the tension is linear. It's T of R is K0 R, where K0 is a constant. And in that case, the equation takes the form dtx is K0 G partial squared alpha of x theta plus alpha d alpha. And due to the second derivative here, this structure of the equation looks very bad to study critical regularity because you have partial squared x is equal to x double prime. And so what is typically done is you integrate by parts once and you put one derivative here, and then you have to take a derivative of the equation, and then you end up putting another derivative on g, and that makes g very singular. And if you're fortunate, you can study it. But I want to show you a trick that we found that we use to provide some cancellation to better understand this. So we introduced this cancellation structure that was not known before, as far as I know. And so we write the equation in an equivalent formulation that will cancel out the terms featuring the bad second derivative. So if you, instead of just integrating by parts against g, if you instead integrate by parts against g1 and leave g2 alone, then this is what you get for the first term. You get delta alpha of x theta, and you have a derivative against all this stuff. And then you leave the second term alone, and then you have a derivative against this stuff over here. And for the first term, you evaluate this derivative inside first before evaluating this derivative. And then you do some calculations and you get this equation here, which is, I claim, much nicer. So it has this kernel, which only involves first derivatives, or the delta alpha of x, which for small alpha is like a first derivative. And it involves the tension of first derivatives, and it involves the delta alpha of x. And so we've canceled out all the second derivative terms. And this cancellation is very important for our analysis, and it doesn't make the kernel extremely singular. So this is our way of writing the equation that's new, and that enables us to do the analysis in our paper. And then, okay, so amazingly, this property of cancellation of the highest order derivatives is also satisfied by the equation for the derivative of x. So if you take partial theta of x and you express that as x prime, and then doing a lot of calculation at the end of the day, you get that there's an equation for x prime, and it's satisfied, and it's right here. So dt of x prime is d alpha over alpha squared times some vector kernel times delta alpha, the derivative of the tension of x prime, where bold-faced t maps R2 to R2, and it's the tension map, which is the tension t of the absolute value of z times the unit vector z, which we're calling z hat here. And here this kernel is a complicated matrix expression that I've written here. I won't read to you yet because I can show you more about it on the next slide. And so this is the kernel. It's k. We call it k of x. and it's x prime dot p. P is a vector. P is a matrix function of d alpha x theta, and matrix multiplied by x prime. And d alpha x is this difference I delta alpha x over alpha, and it's x theta plus alpha over x theta divided by alpha. So sort of quantifying for small alpha, this is sort of x prime, but it's not x prime exactly for not alpha going to 0. And then you have these reflection matrices. P of z is z hat tensor z hat minus z hat perp tensor z hat, and R of z is z hat tensor z perp plus z hat perp tensor z. And then you can write the kernel in this way. So it required a lot of just messing around with the model to find this expression. But it makes writing it this way makes it more tractable to proving a lot of estimates. So I won't read that to you carefully, but there it is. And so our model for the our model for this problem is a vector valued fractional porous medium equation, which hasn't really been studied before as far as we know. Excuse me, I'll have some water. So for small alpha, the integrand for dtx prime is this, and it's approximately like delta alpha of t of x prime over 4 pi alpha squared. And this, when you integrate over alpha, is the fractional Laplacian, the 1/2 Laplacian, the lambda operator. And so therefore the basic model equation for the general tension case should be a vector version of the fractional porous medium equation. So this with t here, this is the fractional porous medium equation. It's fractional because I have the square root of the Laplacian here. And to our knowledge, this equation has not been studied before. However, the scalar fractional porous medium equation has been studied before, and the vector local porous medium equation has been studied here. So if you replace the square root of Laplacian by just the Laplacian, then that's been studied before. And the positivity and monotonicity assumptions that we make on the tension are both physically motivated, as well as the same assumptions that typically appear on the porous medium equation in order to ensure the ellipticity of the problem. So here are some results for the scalar fractional porous medium equation that I won't read to you. And here are some results for the local vector valued porous medium equation that I also won't read to you, but I'll just show you them in case you're interested. And now I'll tell you quickly about scaling critical spaces. So here we have a list of some scaling critical spaces for the Peskin problem under the rescaling x lambda is lambda to the minus 1 x lambda t lambda theta for lambda greater than 0. So the chord arc number, which is an important quantity to this theory, is scaling invariant under this rescaling. The Lipschitz space W1 infinity, the homogeneous Lipschitz space W1 infinity is invariant. The Wiener algebra A1 is invariant. VML1 and VML1 are invariant. All the homogeneous Besov spaces, B dot 1 plus 1 over P, PR, are invariant for any P and R. And we emphasize the role of the space B dot 3 halves 2R and H dot 3 halves due to their L2 structure. So these are scaling critical spaces for this problem. And so I'll tell you some solution spaces for me and for us in this result. So use a LQ, LP, theta mixed space where we integrate in theta first and T outside second for P and Q in the full range. And I'm going to use these Besov spaces without any sort of little belly, just with integrals. And so for S between 0 and 1 and PQR in the full range. You can define the Besov spaces like that. And then we'll also use these Schumann-Lerner mixed regularity Besov spaces where you have an LQ in time with a tilde on it on the outside, because you put the LQ in time norm in here, and then you integrate over beta on the outside, but you also have the difference in beta on the inside here, and the theta interval on the inside. Okay, so these are some of our mixed regularity spaces, and we also have solution spaces with logarithmic regularity, because we're doing the trick that I mentioned to you earlier. So Besov spaces with a little bit more logarithmic regularity are written the same, except for add a mu to the beta -1 in here, but everything else is exactly the same. And here we consider functions mu mapping 0 and infinity 1 infinity, which are increasing. They go to infinity. They satisfy the doubling property, and they don't grow faster than the log, or they grow slower than the log, to be exactly. So mu of r over log of 4 plus r is decreasing. And then this is adding some regularity, but only on the logarithmic scale to these norms. And so this is the scaling critical norm that we'll use in this paper. Is beta the x prime. We study x prime. We study the equation for x prime, and then the critical space is b dot 1/2 2 1, which can be written in this way. And okay, so here is my definition of a weak solution. And basically, if we have initial data in b dot 1/2 2 1, then you integrate against and function with barely enough regularity to make everything finite, and then you integrate by parts formally, and then it gives you the definition of a weak solution, which I won't read to you carefully. And then our definition of a strong solution is a C2 function in all variables that solves the equation pointwise and satisfies the core-dark condition and converges to the initial data in L infinity as t goes to 0. Okay, so this is our first qualitative critical local existence theorem for the fully nonlinear Peskin problem. This is joint work with Stephen Cameron again. So let x be an initial data in such that the derivative is x0 prime is in b dot 1/2 2 1, and the core-dark condition is not 0 initially, and assume the scalar tension T is in C11 locally with the derivative positive for all r, so it's increasing. Then there is a time T such that there exists a unique weak solution x to the Peskin problem, which is also a strong solution. And furthermore, for any beta, x is in C2 beta locally. And additionally, if T is in CK gamma locally for some k greater than 2 and some gamma between 0 and 1, then x is in CK plus 1 gamma locally. Okay, and due to the structure of the equation, x in CK plus 1 gamma locally, we claim is optimal regularity for T and C K gamma locally. We prove this theorem by proving so this is our qualitative theorem, and we'll prove this theorem by proving a quantitative theorem under more restrictive assumptions. And so the quantitative theorem assumes more, but you get more too. So we assume our initial data is bounded in these logarithmically subcritical spaces. The core-dark number is positive initially, and the derivative of the tension map is in W1 infinity, and the tension satisfies an ellipticity condition that the derivative is elliptic. Then there exists a time depending on all these parameters such that there's a solution to the Peskin problem with tension T and initial data And the Peskin problem satisfies a Lyapunov type inequality, like I've written here. And lambda is the square root of the Laplacian. So there's a gain of regularity. And this is the energy inequality that you get. And you also have a quantitative smoothing estimate. So for any small time, x is in C2 beta over tau t between times tau and t with its norm depending upon tau beta and all the previous parameters. And additionally, if the tension is in ck gamma for some k and gamma, then for any small time, the solution is in ck plus 1 gamma with a ck plus 1 gamma norm controlled by all the previous constants. And so we actually have two uniqueness theorems. One says that you're unique in any, for the quantitative theorem, we have uniqueness is in any logarithmically slightly more regular space. And so without adding any assumptions to the tension map or to anything, if you have two solutions in b dot 1/2 mu 2 1 that satisfy the Courtart condition, and if you have any nu, which is a different logarithmic regularity thing satisfying the previous definition, such that nu over mu is decreasing eventually, and it goes to 0. So mu goes to infinity faster than mu. Then for any epsilon, there exists a delta such that if your initial data is smaller than delta, then your solution is smaller than epsilon in the nu space. And so in particular, if x prime minus y prime equals 0 in L2, then the solution is unique in L infinity b dot 1/2 nu 2 1. So if you use a little bit less regularity, then you're unique in that space. And so for example, if you're using the mu quantity, then you can take mu to be mu to the gamma for any gamma between 0 and 1, and you'd be unique in that space. Okay, so we also have a strong continuity estimate that's actually much longer and more complicated to prove. But it also adds an additional assumption on the tension. So if you assume the tension is now, the derivative of the tension is now in W2 infinity instead of W1 infinity, you have the ellipticity condition, then there exists a time depending on all the previous parameters such that you have a Lyapunov type inequality for the difference. So so x prime minus y prime is bounded by the initial data in the norms that you're using. And now this is an equivalent norm to the one you start with. It's not it has the same regularity as the one you started with. And these are the definitions of these norms if you're interested. Okay, so I'm not sure how much time I have, but I don't have that many more slides, so I can just tell you about the proof overview.
We started a bit late, so you can certainly go beyond our 8 o'clock, but let's say maybe roughly another 10 minutes, I would say. If you need more, just let me know.
No, that's plenty. I may not use, I may 10 more minutes from now is plenty. Okay, so the heart of our argument is an a priori estimate as usual, and we make use of our new equation for the derivative of x for x prime, and because the kernel K is symmetric in theta and theta plus alpha, our equation has divergence form symmetry, making L2 based energy estimates a natural first choice. And by making use of Besov spaces, we're interested in then keeping careful track of the time evolution of differences of the form the L2 norm of delta beta of x prime, where beta in the torus is arbitrary. And we have that delta beta x prime solves an equation like this. So the time derivative of delta beta of x prime plus lambda of delta beta of t of x prime is equal to d alpha over alpha squared times delta beta of a of theta alpha of delta alpha of t of x prime. I haven't told you what a is, but calligraphic a is part of the kernel of k. And we calculate that the time derivative of delta beta of x prime, we calculate this, and we get one good diffusive term that's of the form minus lambda delta beta x prime h dot 1/2 coming from the lambda delta beta t of x prime term and using the ellipticity condition, and we get additional error terms. And we then treat the remaining terms as error terms. And there are a lot of error terms. So we're basically left to bound terms that look like this and terms that look like this, where you have an integral over d theta d alpha in both cases. And here you have d beta d alpha of x prime squared, and here you have d alpha of x prime to the power q for example, q equals 1, 2. And here down here you have d beta d alpha of x prime times d beta of x prime times d alpha of x prime to the power q plus 1 divided by 1 over alpha squared. If we were to bound the first term, so the one up here naively, we would get delta beta of x prime in h1/2 and x prime L infinity to the power q, which would make it impossible to close our estimate. This is of the same order as the good diffusive term, but with a possibly large coefficient in front for large data. And we don't have, and so this would have a large constant that we wouldn't be able to absorb into our diffusive term. And okay, so this is the term we were looking at first. However, for this norm b dot 1/2 mu 2, 1, it both controls the size of the norm in b dot 1/2 2, 1, but it also controls the rate of decay. And so for small alpha, the mapping R goes into alpha less than R d beta. This should be d alpha. D alpha of delta alpha f over alpha to the 3/2. This can be bounded readily by f and b dot 1/2 mu 2, 1 divided by mu to the r to minus 1. And this gives you a very, for small r, this gives you a very small constant in front. So therefore splitting the integral in our error term between alpha less than eta and alpha greater than eta for some sufficiently small eta depending on mu, and the initial data in the norm b dot 1/2 mu and other constants, we can bound this error term as epsilon times delta beta x prime h dot 1/2 plus a constant times delta beta x prime in L2. And we can handle this type of error term because now the leading order term has an epsilon in front, and this term is low order. So this can fit into energy estimates. And for the second type of error term, the story is similar, except that we're forced to bound the delta beta x prime in L infinity because it has no decay as alpha goes to 0, since there's no alpha here. Thus, we end up with an error term that looks like this, where you have epsilon delta beta x prime in L infinity, you have delta beta x prime L2, and you have delta beta x prime h1/2 times epsilon. And this L infinity error term at first seems very bad because the Sobolev embedding theorem fails, and the delta beta x prime L infinity is not controlled by our good diffusive piece. So Sobolev embedding theorem fails in L infinity. However, fortunately, once we integrate in beta against mu times beta to the minus 1 times beta to the minus 3/2, we have this quantity. And there is a Sobolev embedding theorem. This is a Besov space type quantity with a mu regularity factor, and there is a Sobolev embedding for this Besov space. And so the logarithmic theorem holds here with the lambda to the 1/2. And we can control this error term at the end of the estimate. And this is, so this saves us. So that's an example of, I mean, this is a long paper, but this is just an example of two terms and how they work. Okay, our high regularity proofs are based on the proof of higher regularity for the scalar fractional porous medium equation in this paper by Vasquez, De Pablo, and Quiros and Rodriguez from 2017. We were happy to find it. And we were able to adapt their arguments to the vector value case into the Peskin problem. Yeah, so I should probably stop here. I also, well, I can tell you very, very quickly. We also proved global well-posedness for the Peskin problem with viscosity contrast. And this is the result with Garcia Juarez and Yoshiro Mori. And it says that if you start out close to a circle with a quantitative constant that you can estimate, then you have a global time solution, and the solution converges to a different nearby circle, and you gain analyticity in these spaces. These are Wiener algebra spaces, and we have exponential convergence to the circle, to a nearby circle, not necessarily the same circle. And it has to be that because it doesn't converge to the same circle. And we can estimate the size of the initial data exactly. And I should say that this kind of behavior, and we do this for viscosity contrast. So the first result was for equal viscosities, and this result is for the full range of unequal viscosities. And this is also for the linear tension law. It's not for the nonlinear tension law. And this is an estimate of the size of the initial data as the viscosity changes. And this kind of behavior near the so 0 is equal viscosities, and near the two endpoint cases is expected, because we don't expect our methods, because the problem is different in these two cases, so we don't expect our method to work in those cases. But yeah, so that's the other results. Let me just say thank you, and if you have any questions, I'm happy to answer them.